just, if I just do it up here, it just doesn't translate. So I'm hoping the lab translates. So I've done that for several semesters now. All right, so we're talking about different chemical compounds. And actually, the other day, we kind of started a list of molecular compounds and ionic compounds. And we said, actually somewhere in there, we said that with regard to bonds, chemical bonds, there's two types of chemical bonds. There are ionic chemical bonds where electrons are transferred, and then there are covalent chemical bonds where electrons are shared. Whether electrons are transferred or shared, all has to do with each atom's trying to get what we call a complete octet. Now, there are some exceptions to that, but octet, of course, meaning 8. That octet we referred to, that NS2, NP6 electron configuration, that's kind of in the crux of where that octet lies too, okay? So we said that we introduced the idea of electronegativity, which is a great vocab term. I'm just saying, for those of you who ate the vocabulary section of my unit exams, who can go wrong with electronegativity? Okay, electronegativity is basically you have atom A and atom B that are going to form a chemical bond, and electrons are either going to be shared or transferred. Okay, we talked electronegativity values are the same thing as Linus Pauling values. Pauling values and electronegativity values are the same. And actually, you have a periodic table that kind of gives you some electronegativity values. And we came up with some delta chi's. The symbol for electronegativity is that fancy X thing, okay? So delta chi is electronegativity difference between atom A and atom B. All right. So if you were to, and I already kind of said this 1.7 out there already, basically if you have a difference that's more than 1.7, then an electron is basically going to jump ship from the lower electronegative atom to the higher electronegative atom. Now, if you go and pick, and I think I've done it before, but if you look at all the Pauling values, electronegativity values, all the nonmetals, remember nonmetals are by far in the minority on the periodic table, it's hard to get a difference of 1.7 or greater. So basically, you pick any nonmetal, join it to any nonmetal, and you're going to go ahead and have a covalent bond. Electrons are going to be shared, okay? The other option is you grab a nonmetal and grab a metal, and you're going to have a delta chi of 1.7 or greater, okay? Your electronegativity difference is going to be greater than that kind of 1.7 threshold. Now, I keep saying 1.7, but depending upon what chemist you talk to and what day of the week it is, they might kind of give you a different, like, cutoff point, but 1.7 is pretty good. Now, what's not up here is what about the metals bonding to other metals? You know, if you're familiar with, I think I might have mentioned this when we talked about solutions, if you're familiar with metal alloys, okay, basically what they are is you take a little dab of this, a little dab of that, you melt it together and you solidify it and you have stainless steel. You have a metal alloy. Well, metals don't chemically bond to other metals. They freeze next to each other from their liquid to their solid state if you kind of get them molten and let them freeze. But basically it's just a solid solution. So metals don't bond with other metals in general. All right, so it's a tug of war, and electronegativity of the atoms will tell you kind of where that electron cloud is going to go. So I like this figure. This basically, wherever you see the red, it's kind of what we say electron rich, and where you see the blue, it's electron deficient. So, of course, we talked about there are 7 elements out there that like to buddy up, the diatomic elements. Chlorine is one of them. So chlorine never runs around by itself. Actually, it's a Cl2 molecule. It looks like this. You could look up the Pauling value for each of these chlorine atoms. They would be the same. So delta chi, electronegativity difference, 0 right there. Okay, that is definitely a chemical bond where electrons are being shared. They're being shared. It's got a special, so that's a covalent bond. It's a special covalent bond. Okay, here we have HCl, the chemical bond between the hydrogen and the chlorine atom. So you can kind of see the little bit of the red, maybe the pink, kind of over there on the chlorine atom. With regard to electronegativity, even if you don't have the Pauling values for electronegativity, I said for the group A elements, okay, that's these 2 and those 6, the group A elements, it increases from left to right and it increases going from bottom going up. Electronegativity. So chlorine's pretty darn electronegative. What that means is the tug of war here with the hydrogen atom, it is going to have its, I call it lion's share of electrons. That's why this little electrostatic map is kind of showing more electrons over there. The last example I have is sodium chloride. Now, I think we chose it as an example, and actually, finally, the electronegativity difference between the sodium and the chlorine, you do get greater than 1.7. An electron's going to be transferred from the metal, which is sodium, to the nonmetal, which is chlorine. Okay, it's almost a stepwise process the way I think of it. That leaves the sodium with as a +1 and the chlorine as a -1, and then you've got that dot, 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 actually that ionic bond between the two. So again, electron rich, the chlorine, electron deficient, the sodium. So that's all that is. Now we are going to talk about kind of a subtle difference between covalent bonds coming up. So actually I told you that kind of covalent bond between the two chlorine atoms is especially sweet. Okay, if the electronegativity difference is 0, okay, we actually call that a totally nonpolar covalent bond. The covalent bond between the H and the Cl up there, okay, it's a covalent bond, but it's what we call polar. And I think I know I talked about this. This is kind of similar to. This is kind of similar to, remember the water molecule? I said the oxygen is partially negative. That's a polar bond between the oxygen and each of the two hydrogens. That's definitely polar. So I'll go ahead and write partially negative up here. We use the lowercase delta. That's a lowercase delta, go figure. So I'm going to put partially negative and partially positive. Okay? Basically, electrons are being shared, but they're not shared equally. Who's got the more lion's share of the electrons that are being shared? The one with the higher electronegative value, which is chlorine. Okay? And then, of course, the top, all I say next to that is an ionic bond. Okay, so the types of bonds. We have 2 covalent bonds, electrons are being shared, and 1 ionic bond here. All right, kind of a similar thing. Electronegativity difference between the chlorine atoms, 0. Nonpolar covalent bond. Electronegativity difference here between the hydrogen and chlorine. Not so much that an electron is transferred. Okay, and then here between the sodium and the chlorine, electron is entirely transferred. And we have an ionic bond between those two things. So this kind of looks at kind of the different types of covalent bonds. Okay, so again, threshold 1.7, I don't know if I always agree with that either. Okay, but clearly kind of, well, if we go with 1.7, we kind of have increasing polarity characteristics leading up from a perfectly covalent bond between the 2 chlorine atoms, nonpolar covalent bond, to something that is strongly polar. Okay, so all 4 of those, okay, all 4 of those examples, electrons are being shared. E shared. Okay, down here, electron is transferred. Bottom line, I can never remember how to spell some words, including the word transferred. 2 N's, 2 F's, 2 S's, 2 N's, I don't know. Close enough. Okay. So honestly, in general chemistry 2, by the way, here's my little plug for general chemistry 2. If you remotely think you might need Gen Chem 2, now's the time to take it. Not just because I think I'm a decent teacher, but while Gen Chem 1 is fresh in your mind. So we are signing up for all spring classes, including general chemistry. But in Gen Chem 2, we're going to start off kind of talking about the polarity of molecules and how that has influences how they behave. So, all right. So this is kind of a rehash over there when I kind of made the 2 columns, the molecular compounds and the ionic compounds. Okay, I said look for the metal, and I kind of drew those spectacles, look for the metal. If you find a metal in that formula, then it's probably an ionic compound. I'd say if you find a metal, it is an ionic compound. I would say that if you find no metal, it still may be an ionic compound. And in tomorrow's lab, I'll kind of maybe show you why that is. Okay. So if a compound's formula contains only nonmetals, it's probably covalent. Remember, covalent and molecular are synonyms, so I kind of go back and forth between the two. Covalent compounds and molecular compounds are the same. Ionic compounds are not. So these are some Pauling values that you might find helpful. These are just a subset of the ones I gave you that you had to kind of look really close on the periodic table for. So this is kind of actually doing well to lead into part 5. So I want you to remember, among the things that we talked about in this unit was this idea of some electrons are more important than others, okay? If you find how electrons are configured, and you kind of, in fact, I have an example coming up here in part 5, if you kind of assemble them in order of increasing n as their subshells, when you identify the highest number of n, actually those electrons are valence electrons. So that actually kind of leads us to the last slide here. What's so special about valence electrons? Well, in the highest energy level n, what an atom wants to do when it's bonding to another atom, whether it gets it by losing electron, gaining electron, or whether it gets it by sharing electrons, or electrons, what it wants to do is have a complete octet. It wants to have this rare gas configuration, this NS2NP6 in its highest energy level n. Okay, so let's see if I click this. Whoa, that was for last semester. This is for you guys. All right, on to part 5. So what I maybe tried to say a little bit, I didn't say it yet, but tomorrow's lab, dry lab, is going to be a little bit, it's one where, you know how you usually do pre-lab and then turn you loose? Okay. Tomorrow's lab is going to be kind of like we're going to step through it and kind of together a little bit, kind of in chunks. And there will be PowerPoint involved, so good, bad, or otherwise. Okay. So let's take a look. This is going to work towards just ionic compounds, and tomorrow's lab is all about ionic compounds. All right. Rare gas configuration. Atoms want to get a rare gas configuration. So you see the JAG, okay? Kind of look at this. Actually, this is the group A elements. You see the first 2 columns. What's missing are the B elements, and then we go over to the next 6, okay? Metals tend to, these are metals, you know. Metals, on this side of the JAG, metals tend to lose electrons to get a rare gas configuration. We'll kind of show you how that works. But in doing so, for instance, lithium and beryllium are going to get the rare gas configuration of helium. Sodium and magnesium, the rare gas configuration of neon. Potassium and calcium, the rare gas configuration of argon. Rubidium, strontium, the rare gas configuration of krypton. So now as I've pulled these kind of pinkish, these, okay, basically what they're doing is getting the rare gas configuration of the rare gas in the period before them. Okay, so for instance, if you pick on argon, where is argon? Argon is actually the period before potassium and calcium. Okay, it's going to kick off 2 electrons, become like that one over there. Okay, let's look at it. So potassium has atomic number 19, so it has 19 electrons. We're going to see potassium actually is going to kick off 1 electron. What's it like then? Well, it's got 18 electrons. It's like argon. Let's take its buddy, calcium. It's got 20 electrons. We're going to see calcium is going to kick off 2 electrons, and 20 minus 2 is 18. What's it going to be like? Argon. That's all I need. That's all I need. And I think, I'm pretty sure, I kind of lose track of when I said things, but didn't we already talk about lithium is group 1A, okay? Starting with beryllium, that's 2A, okay? Starting with aluminum, I'll just talk about the metals, that's actually 3A. 1, 2, and 3. Those actually are the number of valence electrons that those elements have. They kick off all of their valence electrons. I told you a minute ago how many electrons is potassium going to kick off? Minus 1 electron. How many electrons is calcium going to kick off? Minus 2 electrons. 1, and 2, respectively. Oops. So those are the metals. And actually we're going to use a word for that. I think we've talked about that. But as something loses electrons, it becomes positively charged. We call that a cation, not to be confused with a cation. So these form cations. Then I kind of have an analogous thing down here where, again, I kind of focus on the jag. And now actually looking at the nonmetals, which are on the upper right-hand side of the jag. What the nonmetals do are pick up electrons to get like the rare gas actually in their same period. Okay, so let's do this just for kicks. And notice I'm not gonna start with carbon because carbon can kind of go either way sometimes. But if we start with nitrogen, nitrogen is 5A, oxygen 6A, and you know all those are. And fluorine and down is 7A. Okay. So nitrogen is going to pick up 3 electrons. Nitrogen, atomic number 7, pick up 3 electrons. 7 plus 3 is 10. So actually, it's going to have the same. It's going to have the same nucleus, but now it's electron-wise, it's going to be like neon. Okay. So that's how that works. So actually, these nonmetals will pick up electrons to be like the rare gas. Their nucleus is the same. They're just kind of a different version of themselves with different numbers of electrons. So to kind of emphasize this, these are metals, and they will form positively charged cations. You know, if you're trying to remember cations versus anions, ions actually has the little plus there in cations, I think. And these are nonmetals, and they will actually pick up electrons to form anions. And it makes me giggle, I know, never gets old, but it seems like, oops, maybe it doesn't. Anions. So you could almost see where somebody calls that an onions. It's the little things. So this week's lab, we're going to focus on how do you name and make ionic compounds. And then the next week, I think I already told you we're doing a dry lab. Are you warm, Justin? Get some, okay. Next week, we're going to do another dry lab, and we're going to make Lewis structures. It is warm in here. And in Lewis structures, this isn't like a full-fledged Lewis structure, but we'll be kind of doing this sort of approach, where the carbon here represents the nucleus of a carbon atom and the nonvalence electrons of a carbon. Now, if we look at carbon, carbon is 4A, okay, 4A, and so it has 4 valence electrons. That's why there's 4 little dots around there, okay. Going across, nitrogen is 5A. That's why we would have 5 little dots there. Okay, those are valence electrons. Of course, we end up that period with the rare gas, neon. Neon has, and its buddies, group 8A, have 8 valence electrons. They have that NS2NP6 rare gas configuration. Okay. So helium does not have a complete octet, okay? But it does have a complete principal energy level N. When N is equal to 1, it only has 1 subshell, okay? And so you can pick 2 electrons in any S-type subshell, and it's 1s, so it does have a complete. My point is helium is a rare gas as well. All right, so kind of some pictures, some looks at using kind of that Lewis structure idea, or excuse me, that Lewis dot formula idea. So sodium, group 1A, has 1 valence electron. Okay. Sodium, I think I told you before, is actually going to lose its electron, and it's going to look like sodium. It's going to look like neon. Okay. Sodium's got 11 electrons. When it loses 1, it's going to have 10 electrons. Okay. So that's what sodium will do. When it does that, and actually that is the 3s1 electron that goes, 3s1 electron that goes. Now, actually, it's going to have a new valence. It's going to have, if you were to, and we are going to look at it here in a minute, what does its electron configuration look like now? And Na plus or plus 1, what does it look like? And it's actually going to have the same electron configuration as the element neon. And the element neon has a complete octet. So let's look at a couple of nonmetals. So sodium was a metal, it lost an electron. Fluorine is a nonmetal. Specifically, it is 7A. That's why you see 7 little dots around there. Okay, to get a complete octet, it's going to pick up an electron, and it's going to look like this. Okay, so now fluorine has the same, actually we're going to call that the fluoride ion. This fluoride ion has the same core as a fluorine atom, but it has the electrons like a neon atom. It's like a hybrid. Pick on sulfur, which is also a nonmetal. Sulfur is group number 6A. That's why you see 6 dots there. It's going to pick up 2 electrons to get a complete octet and have the rare gas of argon. Sorry, have the same electron configuration as the rare gas argon. So this is kind of what it looks like. All right. So what we've been talking about are, and tomorrow we're going to talk about not only just monoatomic ions, but polyatomic ions. But a monoatomic ion is basically an atom, a metal that loses electrons, or a nonmetal that gains electrons, single atom. And we've kind of talked about this, that you get these 2 different options. A cation is positively charged. Your metals are going to form cations. They're going to lose electrons, or electrons. An anion is negatively charged, okay? It's going to pick up an electron or 2. Those anions come from the ground. Anions come from your nonmetals, okay? But just to emphasize, remember that the nucleus stays the same. No touching the nucleus. No nuclear reactions going on here. Monoatomic ions. So sometimes, on your next unit exam, you're going to have your periodic table. You won't need your calculator on your next unit exam, okay, but you're going to have a black and white periodic table. Sometimes what students will do is like mark at the top of the groups, okay, something that will help them remember. Let's see. So if we start with the metals, and I want to only focus on the main group metals. So main group means A, so group A metals. Those 2 columns and those 6 columns. So if you're talking metals, you have to be careful to look for the JAG. The JAG, right? So starting with aluminum. And like I said, they're going to lose all of their valence electrons. Now, their new, and we're going to look at some electron configurations, their new electron configuration is going to show you that their highest N is now N-1. So I'll show you what that looks like. Okay, so like I said, sometimes people will take this 1A, and you could include hydrogen if you want. Remember, hydrogen is in actually, and this is kind of, we're getting to why actually on my periodic table I have hydrogen in 2 places. But some students will put a +1 up here, and actually tomorrow's lab I'm going to kind of emphasize that. These all will form a +1 charge, okay, if they're going to do anything with regard to forming an ion. If we go over 1 column, okay, starting with beryllium, these 2A are going to kick off their 2 valence electrons, and if they're running around now with 2 less electrons, they're going to have a +2 charge, okay. So sometimes people will put a +2 charge there. And then skipping over to the 3A metals. So you can't do boron, because boron is a nonmetal, okay? So starting with the 3A metals, okay? Now notice I don't, and I need to double check why I don't, but notice I don't have indium and, is it tellurium? Tellurium's Te. Thallium? Okay, I don't have indium or thallium listed there. I'm not sure. There are some atoms, some elements that don't follow the general rules. But aluminum and gallium will lose 3 electrons. 3A means they have 3 valence electrons to lose. They'll lose 3 electrons and become a +3 cation. So let's take a look at how electron configurations kind of iron out. So we talked earlier that sodium is atomic number 11, and so here's how the 11 electrons around a neutral sodium atom are configured. 1s2, 2s2, 2p6, and it peters out at 1 electron in the 3s, so 3s1. Now, if I told you that it was going to lose an electron, one of the things, and I think I'm going to emphasize it even more here in a minute, that 1 electron that's lost as it goes from a neutral sodium atom to a +1 sodium cation has to come from the highest n. So the highest n is 3. So actually that's why when I rewrite this, all that's missing is the 1 electron in the 3s. So the electron configuration of the sodium cation is 1s2, 2s2, 2p6. So a few slides ago, I kind of told you that it would be, its new valence shell would be the n-1, okay, ns2, np6, okay. So the n-1 means it was 3 and now it's 2, okay. Let's look at aluminum. So aluminum is atomic number 13. So a neutral aluminum atom would look like this: 1s2, 2s2, 2p6, that gets you up to 10 electrons, and then 3s2, 3p1, so that's 13 electrons. And I told you that put above the aluminum and gallium anyway, a +3, it's going to form a +3 cation. The 3 electrons that are going to go are right here. These 3 electrons right here. So we could write the electron configuration of the aluminum +3 cation, and it would be 1s2, 2s2, 2p6. So not so surprising. Okay, they're in the same period. I said that this is like neon, and this is like neon. I have a slide coming up, and again, it's another favorite vocabulary word of mine. It kind of rolls off your tongue. These cations are called isoelectronic. Isoelectronic. It simply means that they have arrived at the same electron configuration. It just happens to be like neon. So when I say isoelectronic, I'm really talking about, you know, these guys. The cations are isoelectronic. Neon is isoelectronic with them, but all right. Cool. So remember, put blinders on if you need to, but the valence electrons are always the highest n, the highest n. And so, like on a test, sometimes I've done this before, if I ask you to write the electron configuration of a neutral atom, and then I ask you to write the electron configuration of that same element, but it's now a cation, it's going to lose some electrons, or 1 or 2 or 3, or however many its new charge is, okay? And the ones that are going to go are the highest n. The highest n. All right. There is a little subtle difference there, too. When we looked at aluminum losing 3 electrons to become aluminum +3 cation, technically the first electron to go was in that 3p subshell. I know it's kind of silly. But remember we said that the S and the P have values of L is equal to 0 and L is equal to 1 respectively. You know, the P value, the P has a higher L value than the S. So if you're going to get picky with pulling electrons, you know, valence electrons off, that's how it goes. So let's look at iron. Iron is atomic number 26, so the 26 electrons are configured this way. Actually, the first list, sometimes students say, do I have to reorganize it? But to me, this is actually, when I grade your test, this is in the order of adding. Specifically adding using the arrow diagram. Okay, and I guess to answer your question, do you need to rearrange them? Not necessarily, no. But I've rearranged them here to emphasize what is the highest n. Okay, so the highest n actually is an n value of 4. We have one subshell that is 4s. Okay, so one form of iron actually, you're going to see iron has two oxidation states. The iron can actually form a +2 cation and a +3 cation. If it forms a +2 cation, those two are the electrons to go. Okay, so basically we rewrite it minus the 2 electrons in the 4s. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Now its highest n is 3, and hopefully you can see that, that octet in there. You can see that ns2, np6 electron configuration. Anything else, that's fine, tagging along. All right, let's kind of piggyback from our Fe+2, kick off one more electron to get Fe+3. Kick off one more electron. Now, I told you that if you have a choice here, in the same N, okay, you have to have the highest L value. So the L value of S is 0, the L value of P is 1, the L value of D is 2. Okay? So that one last electron is actually going to go from here. Which, is that not beautiful or what? What happens, and I'll go ahead and rewrite this, okay? What happens when you have only 5 electrons in a D subshell? Oh my gosh, it's like a harmony thing, okay? Any D-type subshell has 5 orbitals, so 5 electrons. It's like, awesome, okay? So that actually is how the electrons are configured in an Fe+3 cation. So yeah, on your test, if I do this, and I probably will, how are the electrons configured in a cation, I will usually give you the neutral atom first, and then have you pick off electrons. Okay? All right. So let's look at the nonmetals. We said nonmetals will pick up electrons to get like the rare gas in their same period. So the nonmetals, I kind of skipped group 4, go on to group 5A, okay, and actually 5A will pick up, let's see, 5A means 5 valence electrons. Octet is 8, so 5 plus 3 is 8. They're going to pick up 3 electrons. 6A are going to pick up 2 electrons, 7A are going to pick up 1 electron. That's it. That's totally it. Okay. So sometimes students, when they get their sheet for their Unit 4 exam, will find the 5A and write a -3 up there, okay? That's because they actually, those guys, and I don't have arsenic here, probably arsenic's more obvious to me, because remember we talked about metalloids? Metalloids are kind of along the jag. Actually, arsenic is a solid metalloid. So nitrogen, phosphorus will pick up 3 electrons, become like neon and argon, respectively. Oxygen, sulfur, and selenium. I think selenium too. I don't know why that's not on there. They pick up 2 electrons and become like their rare gas in their period. Okay, so a lot of times students will put a -2 up there because they become negatively charged. Hydrogen, actually, hydrogen can either kick off its 1 electron or pick up another electron. Okay, if it picks up another second electron, guess what? It's like helium. Dun, dun, dun. It's called the hydride anion. But not assuming hydrogen isn't listed twice, beginning with your halogens, okay, 7A picks up 1 valence electron, has 7 valence electrons, it picks up 1 other electron, and it gets a complete octet. So a lot of times students will put a -1 over in that column. So tomorrow, actually, this is helpful because tomorrow we're going to be dealing with that. For these monoatomic ions with just 1 atom, what sort of charge are they going to form? Find them on the periodic table for if they're a group A elements. Okay, so let's look at electron configurations. For chlorine, we're looking at its atomic number 17. So the 17 electrons are configured this way. Now, I am going to use the abbreviated rare gas notation. So I'm going to use a box, put neon in it. So beyond neon, I need to accommodate neon's 10 electrons. I need to find homes for 7 more electrons. So this is what chlorine looks like. It has that block of 10 electrons for neon. And then beyond that, it has a 3s2, 3p5. So the halogens, that's 7a, that's where chlorine is, picks up 1 electron, okay? So now, and for some reason, when you have anions, we actually, and I'll emphasize this tomorrow, but Cl is chlorine, and for the monoatomic ion of chlorine, you drop the ending and replace it with IDE. So instead of INE, chlorine, it's IDE, chloride. So my point is, the chloride ion, okay, has the same root 10 electrons of neon, and then it has 3s2, 3p6. So let's pick on phosphorus, which I was double checking. Yeah, phosphorus is in the same period as chlorine, so it's going to be based on the same noble gas neon. So phosphorus has, how many electrons does it have? It's like 15 electrons. Okay, so this right here, when we do bracket neons, that's 10 electrons. So we need 5 more electrons, and there'll be 3s2, 3p3. Of course, phosphorus having 5 valence electrons, it's going to pick up 3 electrons and form a -3 charge. Okay, so here we go. The phosphide ion, we call this phosphide, we call that chloride. The phosphide ion now has the 10 electrons of neon. Beyond that, it's 3s2, 3p6. So again, the term isoelectronic fits very well here. I could draw arrows to the 2 things that are isoelectronic. Isoelectronic. They have the same electron configuration as argon. Everybody loves argon. It's the pirate element. Okay, so that's kind of how that works. So we have a lot of electrons coming and electrons going. Electrons are coming to form anions for the nonmetals, and electrons are going to form cations for the metals. Okay? So with all these electrons kind of coming and going, we definitely have species, I like that word here in chemistry, I know they use it a lot in biology, but we have species with the same number of electrons, and they're sitting or configured the exact same way. So all of these actually are isoelectronic with neon. Neon has 10 electrons, and they're configured 1s2, 2s2, 2p6. Okay, and if you look in the same period as neon, okay, same period as neon, you have these 3 species that are gaining electrons, the same period. The period beyond neon, you have these 3 things that are losing electrons. So gain electrons, lose electrons. These are the nonmetals, and these are the metals. Pretty good. So tomorrow you are going to be, I told you we're going to be kind of sticking together, kind of walking through it. There's 3 parts in tomorrow's lab. And everybody works kind of at a little different pace. So we'll do part 1, and I'll let you work for a little bit. I'll introduce part 2, let you work for a little bit. And then part 3, I'll just meet you on the other side for after part 3. But we're going to start out with this binary ionic compounds, binary meaning 2, okay? And we're just going to start with taking I just love these. We're going to take a metal, and we're going to take a nonmetal, and we're going to put them together. It's a wonderful thing. It's like closets. I tell students, you have a closet of metals, you have a smaller closet of nonmetals, and you mix them together to make an ionic compound. It's so fun. So tomorrow we're going to actually look at how do you come up with a formula for that ionic compound, write the formula. The other thing is how do you name the formula. So I just want to kind of take a look at how do you make the formula here. Okay. When you make the formula, the formula of your compound needs to be neutral. Okay. Remember that crystalline lattice structure that we kind of looked at before? Basically, your overall, where it alternates cation, anion, cation, anion, cation, anion. Okay. Your overall thing needs to be neutral. So your pluses and your minuses need to be a wash. Okay. I'll kind of show you what that looks like. So sodium has 1 valence electron. Fluorine has 7 valence electrons. Okay. What we know is that sodium will kick off its valence electron. Okay. And so it will become a +1 charge and a -1 charge. Aside from all of that diagram, because you're like, oh my gosh, if I have to draw a diagram like that for every ionic compound, I am going to go insane. Okay, aside from that, we can actually, I say, evaluate that formula to see if it's neutral. Okay, sodium, we know because it's 1A that's going to form a +1 charge. Fluorine, we know because it's 7A, it's going to form a -1 charge. Sometimes I tell students you can check for neutrality this way. I have 1 sodium, it forms a +1 charge. I have 1 fluorine atom, it forms a -1 charge. Okay, I'm not real handy without a calculator, but I think I got that one. It's neutral, that's all I mean, okay? So let's look at the next one. Okay, sodium, again, on either side, getting ready to pounce on the sulfur. Sodiums have 1 valence electron. Sulfur has only 6. So can you almost see these, like these guys parking right there? Okay. But what I want to do is kind of check for neutrality. Let's go back up to the formula for sodium sulfide, and we'll talk about how do you get the name sodium sulfide. Okay. Let's check for neutrality. So sodium, okay, I know it's going to form a +1 charge. Why? Because it's 1A. Sulfur, I know it's going to form a -2 charge. Why? Because it's 6A. Okay, if I want to check for neutrality, I take 1 sodium atom. Oh, sorry, oops. How many sodium atoms do I take? I take 2. 2 sodium atoms times +1 each, plus 1 sulfide ion, plus -2, okay, it's a wash. It's neutral. It is neutral. So that's kind of how that works. So I like to finish up this, and this usually works pretty good for students. The thing that makes the size of an atom or a species actually is the electrons, okay? So this probably makes sense. If something's losing electrons to form a cation, it's always going to be smaller than its parent atom. It always is. And similarly, if something's gaining electrons to become an anion, it's always going to be larger. The anion's larger than its parent. That makes sense. It's got more electrons. Okay? I think we don't have enough time. Okay, we're going to pick up here probably like we're going to pick up here on Friday. Okay, but this is all good to get under our belt.